What I would like to discuss today are types of discontinuities that you will see throughout calculus, and hopefully had some of these discussions in your prerequisite courses. You will see two types of discontinuity that we tend to work with quite a bit in Calc 1, non-removable discontinuity and removable discontinuity. And they will be very self-explanatory as to which one is which as you go through. Non-removable physically means that we could not do, what students typically call fancy algebra to remove it. There was nothing we could do to remove that discontinuity algebraically. Removable tends to mean that we did something algebraically and we removed that discontinuity. Also, numerically, they look very different. The non-removable discontinuity numerically will look something like 5 divided by 0. I have some non-zero value over 0. There's typically not much I can do with that algebraically. That says a whole lot. Versus 0 over 0 for the removable. So again, that is sort of the calculus conversation that you will have. The 5 over 0 versus 0 over 0. You may have that conversation early or late on in calculus, but that has a lot to do with our limits and a lot to do with our discontinuity types. Graphically, what you will see is the non-removable discontinuity, the first one that we will talk about, looks like our vertical asymptotes. And so these are physical jumps in my function where there is certainly no x value that can be calculated, and there is no hole. Literally, I have a jump. So typically what happens is you might be going up to positive infinity on the left of that vertical asymptote. Then you're either starting at positive infinity on the right hand side of it if it was an even multiplicity of that vertical asymptote, or you're starting down at the opposite side if you were an odd multiplicity of that vertical asymptote. And we'll talk about multiplicities of roots and things as we go through. So my first example for you for non-removable discontinuity is y equals the function 5x over the quantity x minus 3. There is nothing, I cannot physically touch those x values and reduce them in any way algebraically because the x minus 3 is part of that binomial in the denominator, so I certainly don't want to do anything algebraically that it would not be legal. And so there's nothing algebraically that I can really do to this right now to simplify it any, and again, I'll see this when I get to limits. If I physically put the limit value in, I would see that it is a non-zero number over 0, so I would know that it's non-removable as well. And so what I'm looking for here is, where is the denominator 0? Excuse me, it's not 2, it's 3. So where is x minus 3 equal to 0? That's where this discontinuity will occur. And so you can write this one of two ways. I can write x minus 3 equals 0 since I'm solving that equation, or I can physically say, I know x minus 3, that my denominator cannot be 0. You cannot divide by 0. And so x cannot be 3. And so what I end up seeing graphically is I end up seeing a vertical asymptote, which I will denote as VA, at x equals 3. And so my graph will show that numerically. When I get to limits, it'll show that, and algebraically I could not remove anything. That shows up as a vertical asymptote. Another example might be this 2 divided by natural log of x. And so what I would see graphically if I looked at this, if you're more of a visual person, is the domain, because again, you should not be having discontinuity discussions without involving the domain. And so x, because that's in the argument of natural log, has to be greater than 0, and so I know I have a hole because it cannot equal 0. And so I have a hole at 0, and then this will go down pretty sharply. I will have a vertical asymptote, which we'll talk about here in a second. And then the rest of the graph appears up here. Okay? So that's what the graph will look like. So if you're a visual person and you need the graph to sort of help you make sense of the algebra, then there you go. So what does the algebra look like? Well, again, I cannot divide by 0, so let's take a look at, I'm going to say natural log of x cannot be 0. And if you need to see this where you're solving, you could raise, e to the both sides. That would still be equivalent. Or you can just use your change of base because this is log base e. So you get to e to the 0 is equal to x. Or you could just know that if your argument is 1, natural log of 1 is 0, so I know x cannot be 1. And so that's where my vertical asymptote is, because again, this was non-removable discontinuity. The other thing I want to mention is the domain, right? The domain of this function would, not negative infinity. I'm so used to starting at negative infinity. For this one, right, we start at 0, but we cannot include 0. Right? We talked about that. You can't have a negative argument of natural log. And then we have to make a stop at 1, and we have to jump over and go on the other side of 1, and then it looks like we're going out to positive infinity, which we can again verify later. Okay, so now the other type of discontinuity is removable, and these look very, very different graphically. The non-removable, again, turns out to be this line, whereas the removable is a hole. And again, numerically, if I look at it, it becomes 0 over 0, but graphically it will look like a hole. And so you actually had a question that I think you've explored prior, so I actually want to look at my example 2 first and see if we can explore this one and see if this makes sense first. If I gave you algebraically this y sub 1, and I said, is y sub 1 equivalent to y sub 2? Most people start at this point in their math career and say, well, I know how to factor the difference of squares x squared minus 4 into x plus 2 times the quantity x minus 2, and then I know I can reduce the factor x plus 2 over x plus 2, so I know y1 is indeed x minus 2, so sure, isn't y1 equal to y2? And the answer to that is they are not necessarily equivalent because of domain. So if you were writing domain of y1, you actually have to make a stop anywhere your denominator is 0. It doesn't matter the type of discontinuity, it's still a jump. It still cannot be included in your domain. So my domain would be negative infinity to negative 2, and then I go negative 2 to infinity. So I can have any other number except for negative 2. Versus my domain for y2 is all reals because it is a line. And linear functions don't have restricted domains. And so because these domains are not equal, one is definitely restricted, right? It cannot be negative 2. I would say these functions are not necessarily equivalent. But what I can say is on my graphing calculator, they're going to look very, very similar. y2 I can do first. It has a y-intercept of negative 2. Right? It has a slope of 1, so I'll see it also cross positive 2. And so it looks like this line right here. Okay, this is y sub 2. Y sub 1, on the other hand, if I graph it in my graphing calculator, I see almost the exact same line. It appears that it just traces the y sub 2. So I think they're both there. And so sure, they look equivalent. But if you look at the table of values, or if you actually zoom in surrounding the discontinuity, right? X cannot equal negative 2. Remember we said that from above or from the domain. So if I physically take a look at negative 2, on the y1, the green line, I have a hole. And forgive me, it should be kind of down here. So I have a hole. And yet on y2, I do not have a hole. Here's no hole. And this function has a hole. Okay, so that is the removable discontinuity and what it looks like. So I would say function y1 has a hole at, and if I want to find the physical point, this is again the same line as y2 equation-wise, right? Equation looks the same. So I can put -2 in here or in that reduced, right, y1. And so when I do that, -2 minus 2 is at -4. So my hole is at -2, -4, which is why I kind of knew that my tick marks were, oops, a little off here. Okay? And so this -4 is going to become very important as we get into calculus a little bit further. Last example I'll go through with you is a little bit repetitive, so I'll go a little bit quicker. If I want to take a look at this function to see if it has removable or non-removable discontinuity, I would try to do any algebra that I could first to see, oh, indeed, the x factors will remove. And so I have the placeholder of the 1, or the factor of 1 left over. And so here is my function. So I actually have two non-removable at x equals 3 and x equals -3. So graphically those are vertical asymptotes. But I physically removed one type of discontinuity, and so I removed, so removable x equals 0, right? That's where that factor would be 0. And so that will turn out to be a hole. And again, if I put 0 in, I can determine where the hole would be. And so, because this function does not have any issues, this ending simplified fraction or rational equation does not have any issue with x being 0. So if x is 0, I get -1/9. And again, that y value is going to be, of the hole, is going to be very important for us to find in the future here. Thank you. I hope you find this video on types of discontinuity helpful, especially as we move forward and have those calculus discussions.